Okay, so hello everyone, and welcome for this last SIPTA virtual seminar of this year 2024. So today we are very happy to receive Frédéric Pichon, who is a highly regarded expert in belief functions and all that is related to it, that will talk mainly about information fusion. The talk today will be shared by Thierry Deneux, another prominent person in uncertainty reasoning and in particular belief function. Thank you, Frédéric, for giving the talk, and thank you, Thierry, for accepting to chair the seminar.
Okay, thank you, Sébastien. Good afternoon, everyone. So I'm very happy today to introduce Frédéric Pichon. So as Sébastien said, Frédéric is one of the best specialists about belief functions. He graduated from the University of Compiègne in 2009, and I was lucky enough to be his supervisor at this time. And he got the habilitation in 2018, and he's now a full professor at Artois University in Béthune, France. And he's working on belief functions applied to uncertain reasoning, information fusion, machine learning, and also statistical inference. Okay, so I'm very happy to leave the ground to Frédéric, who will tell us about, I think, an overview of his work on information fusion with belief functions. So, Frédéric, please.
Thank you, Sébastien and Thierry, for this very kind introduction. And thank you also to all that are involved in the organization of this event and for the invitation to give this talk. So I am a member of the Laboratory of Computer Engineering and Automation of Artois, which is a laboratory of Artois University, and that is located in the north of France, in the city of Béthune. So it's a great pleasure for me to give this talk on the topic of the combination of evidence, a topic that I have been interested in for some time now. So I guess most, if not all of you, know that Dempster's rule of combination is the cornerstone of Shafer's theory of evidence. So it allows the combination of independent and reliable pieces of evidence. And in this talk, I will present some extensions of Dempster's rule, allowing us to account for various assumptions with respect to the reliability and dependence of the pieces of evidence. So specifically, I will first provide a general approach for the fusion of independent pieces of evidence, which permits a refined form of the lack of reliability. And then I will describe a means to specify the dependence when combining reliable pieces of evidence, in a particular yet important case where they are elementary. That is, they are represented by simple mass functions, also known as simple support functions. And along the way, I will present some theoretical and practical interests of these extensions. In particular, I will spend some time at the end of my talk to present an application of being able to account for the dependence between elementary pieces of evidence. Okay, so my talk will be divided into two parts accordingly. So in the first part will be dedicated to assumptions about the reliability of the pieces of evidence, and then the topic of the dependence will be handled in the second part. But first, in order to be able to discuss combinational rules in the theory of evidence, I need to recall a few things, and in particular, how pieces of evidence are represented in this theory and how Dempster's rule is obtained, which is what I will do now in this background part. So in Shafer's theory of belief functions, a piece of evidence about a variable x, taking values in a finite set of theta, called the frame of discernment, is typically represented by a mass function, which is a mapping from the power set of theta to the unit interval, such that the sum of the masses allocated to the non-empty subsets of theta equals 1, and such as the mass allocated to the empty set equals 0. So the mass M of A represents the probability that the evidence supports exactly the proposition x belongs to A, and nothing else more or less specific. And the subsets of theta that receive a positive mass are called the focal set of the mass function. Furthermore, a mass function is said to be non-dogmatic if theta is a focal set, vacuous if theta is the only focal set, in which case it corresponds to a totally non-informative piece of evidence. It is said to be Bayesian if its focal set are singletons, in which case it corresponds to a probability distribution. And finally, it is said to be simple if it has two focal sets, so theta and some strict subset A of theta. So in the theory of evidence, a mass function, to quote Shafer, involves a probability model for the evidence bearing on X. Specifically, the semantics for arbitrary mass functions proposed by Shafer rely on the following canonical model. So suppose we receive an encoded message containing information about X. So more precisely, the actual code used is unknown, but we know that it was one in a finite set big omega, as well as the chance p omega of each code omega being selected. Furthermore, we know that the meaning of the message is X belongs to gamma of omega, with gamma of omega a non-empty subset of theta if code omega was used. So the tuple omega p gamma represents then the available information. Now, given such information, we can remark that for any non-empty subset A of theta, the probability or total chance that the message means X belongs to A is the probability of the code whose meaning is A. Okay. So in other words, the knowledge about X induced by the randomly coded message is represented by a mass function, and we can of course generate any mass function in this way. So Shafer semantics for a mass function is that it is obtained by comparing the evidence about X to a hypothetical situation in which we receive a randomly coded message, that is by fitting the evidence with such tuple omega p gamma. And let me remark that formally such tuple is a random set. And in this presentation, we will encounter several such tuples representing the available information and components of some finite sets, a probability measure on the finite set, and a multivariate mapping from the finite set to theta. And in general, I will refer to them as random sets. And I will also refer to the mass function obtained from a given random set using such an equation here as the mass function induced or generated by the random set. Okay, so we can now turn our attention to Dempster's rule. So specifically, I will recall how it can be derived using the semantics of mass function that I just provided. So let us consider the following situation. Let omega1 p1 gamma1 and omega2 p2 and gamma2 be two messages representing two pieces of evidence about X and inducing mass functions m1 and m2 respectively. So assume that these messages are independent, which means that the joint probability p12 of omega1 omega2 that the pair of codes omega1 omega2 was chosen is equal to the probability of omega1 being chosen and of the probability of omega2 being chosen. Assume in addition that these messages are reliable, which means that if the actual codes were omega1 and omega2, then we can conclude for sure that X belongs to the intersection of the meanings of the two messages using this under these codes, which I will denote here by a multivariate mapping gamma intersection from the joint codes to theta. Now, remark that the decoding of the encoded messages a method of something. So indeed, if this intersection leads to a logical contradiction, then we know that the pair omega1, omega2 could not be the pair of codes actually used. And thus, we must condition the chance distribution on to eliminate such pairs. That is, we must condition the distribution on the pairs of codes that yield non-contradictory interpretations, which is this event here denoted theta intersection. So let me denote by P intersection the probability measure resulting from this conditioning. Then we have that under the assumptions that the pieces of evidence represented by mass functions m1 and m2 are independent and reliable, our knowledge about X is represented by the mass function denoted m1 or plus m2, which we call the orthogonal sum of m1 and m2, and induced by the random set omega1 times omega2 P intersection gamma intersections, which represents all the available information. That is, under these assumptions, the probability of knowing that X belongs to A is, which we denote by m1 or plus m2 of A, is the probability, according to probability measure P intersection, of the pair of codes for which gamma intersection yields A. Now, one should note that the orthogonal sum is well defined only if P12 of the event theta intersection is positive. And a similar condition will hold for all the combination schemes that I will present in this talk. Furthermore, it is easy to show that the orthogonal sum of M1 and M2 for the subset A is equal to the sum of the products M1B, M2Cs for all Bs and Cs such that their intersections are equal to A, divided by 1 minus the probability to obtain a contradiction, which is nothing but the sum of the products M1B, M2C for all Bs and Cs whose intersections are empty. And of course, as you may already know, the binary operation O plus here is called Dempster's rule. Okay, so what we have just recalled is that the assumptions leading to Dempster's rule are that the pieces of evidence to be combined are independent and reliable. Now, these assumptions clearly do not always hold, and what I will present in the remainder of this talk, as I mentioned at the beginning, are extension of Dempster's rule, allowing us to account for various assumptions with respect to the reliability and dependence of the pieces of evidence. And I will start by covering the case of the reliability, still assuming the pieces of evidence to be independent. So the reliability of a piece of evidence is classically understood in terms of relevance. That is, it is reliable if it provides useful information regarding the variable of interest. So, for instance, a broken watch is useless to try and find the time it is, since there is no way to know whether the supply information is correct or not. So it is not reliable for the time. And my 10-year-old son is ignorant about the name of the latest Nobel Peace Prize laureate. He is not reliable for this question. So the basic idea here is that a piece of evidence is valid if it is reliable, whereas it is useless if it is unreliable. So we'll now see how we can formalize this basic reasoning. So let us first consider a very simple case where we have a single piece of evidence, and this piece of evidence corresponds to a message, meaning X belongs to some subset A of theta. Now, if it is unreliable, then it is useless, and we know nothing. That is, we only know that X belongs to the frame. Whereas if it is reliable, then we should accept it. That is, we can deduce that X belongs to A. So formally, let R be the variable denoting the reliability defined on calligraphic R, where rel means that the piece of evidence is reliable and unrel means not reliable. Then the interpretation of the message X belongs to A, according to the reliability, may be modeled by a mapping pi A from calligraphic R to the power set of theta, such that we have pi A of rel equals A and pi A of unrel equals theta. That is, when a piece of evidence is reliable, we should deduce X belongs to A, and when it is not reliable, then we know nothing. That is, we only know that X belongs to the whole frame. So let us now consider the following more general case. First, the piece of evidence now has an uncertain meaning. That is, we receive a message omega p gamma, which induces a mass function M. And secondly, this piece of evidence is only partially reliable. That is, its reliability is uncertain, with alpha the probability that it is not reliable. So what can then be inferred about X? And we can remark that if the accurate code was omega, and the message is reliable, then we know that X belongs to pi gamma omega of rel. Whereas if the message is unreliable, then we know that X belongs to pi gamma omega of unrel. That is, we just know that X belongs to the frame. Hence, the probability to know that X belongs to some strict subset A of theta is clearly equal to the probability of the message being reliable times the probability of the codes whose interpretations are A under the assumptions that the message is reliable, which is nothing but the probability of the codes which mean X belongs to A, and thus the probability of knowing that X belongs to A is simply 1 minus alpha times M of A. So if we want to be a bit more formal, we can remark that the available information in this situation is represented by the random set composed of the Cartesian product of omega and calligraphic R, and of the product measure P times PR, and of the mapping gamma calligraphic R from omega times calligraphic R to the power set of theta, such that gamma calligraphic R of omega and R is equal to pi gamma omega of R for all pairs gamma R. Omega R, sorry. And so we can remark also that the knowledge it induces about X is represented by the mass function alpha M, which I showed on the previous slide. Furthermore, this mass function alpha M is nothing actually but the result of Shafer's discounting with discounted alpha of the mass function M. So I do not have time to go into the details, but let me mention that the notion of unreliability can be refined into a notion of contextual unreliability, which leads to a more general model for the correction of a piece of evidence that includes, as particular case, also the contextual discounting operation introduced by Mercier and colleagues. Yeah. So another refined form of reliability is when we assume that the reliability includes another dimension besides the relevance, which is the truthfulness. So being truthful means actually supplying the information possessed. Now, the lack of truthfulness can take several forms. and can be intentional or not. So for instance, a sensor that has a systematic bias is a kind of unintentional lack of truthfulness. But I will consider in this presentation only the crudest form, where non-truthful means telling the contrary of what is known. And it is a simple model, but as we will see, it is particularly interesting when considering several pieces of evidence. So let us see how we can formalize this two-dimensional reliability. So assume a piece of evidence corresponding to a message whose meaning is X belongs to A. Now, if it is not relevant, then it is useless, and we know nothing. That is, we know that X belongs to the frame. Whereas if it is relevant, then either it is truthful, in which case we keep X belongs to A, or it lies, in which case we replace X belongs to A by X belongs to the complement of A. So let R be the binary variable denoting the relevance, and T the variable denoting the truthfulness. And calligraphic RT is in the space of the possible states with respect to the relevance and truthfulness of the piece of evidence. And the interpretation of the message according to the relevance and truthfulness may be modeled by a mapping pi AT from calligraphic RT to the power set of theta, such that if the piece of evidence is relevant and truthful, then we deduce X belongs to A. If it is relevant but not truthful, we deduce X belongs to the complement of A. And if it is not relevant, we simply know nothing, whatever the truthfulness, which corresponds to these last two cases here. And similarly, as for the previous reliability model, uncertainty, both with respect to the meaning of a piece of evidence and its relevance and truthfulness, can obviously be considered. And I won't detail it here, but I will just mention that it leads to a generalization of discounting. And let me also mention that refined forms of the lack of truthfulness can be taken into account, which amounts to contextualizing the non-truthfulness, similarly as we can contextualize the unreliability. Okay, so now that we have seen how to formally represent the lack of reliability for a piece of evidence, let us consider the case where we receive several pieces of evidence. And more specifically, I will focus on a case where we receive two pieces of evidence, but what I will present here can readily be extended to more than two pieces of evidence. So similarly as for Dempster's rule, consider the following setting. Let omega1 P1, gamma1, and omega2 P2, gamma2 be two messages representing two pieces of evidence about X and inducing mass functions M1 and M2 respectively. And assume that these messages are independent, which means that the joint probability P12 of omega1, omega2 that the pair of code omega1, omega2 was chosen is equal to the product of the probability of omega1 being chosen and of the probability of omega2 being chosen. And let's R1 and R2 be the variable representing the reliability of the two messages according to the simplest definition of the reliability. And let's calligraphic bold R represent the four possible situations, that is the four possible assumptions with respect to their joint reliabilities. Furthermore, assume uncertainty in the form of a probability distribution on the reliabilities. Then our knowledge about X may then be defined as the mass function calligraphic R bold M induced by this random set here, where gamma subcalligraphic R bold is a mapping from the joint codes and the joint reliabilities to the power set of theta, which models the fact that if the actual codes were omega1 and omega2 and the messages were in the reliability state R bold, then we know for sure that X belongs to the intersection of the interpretations of the two messages given the assumptions on their reliability. And where P subcalligraphic R bold is a product measure of the distributions on the code and on the reliabilities, conditioned on the tuples of codes and reliability states that yield non-contradictory interpretations. So this conditioning is due to the fact that if the decoding according to some pair of codes omega1 and omega2 of the encoded messages leads to a contradiction given some reliability state R bold, then we know that this pair of codes together with this reliability state could not be the actual ones. So this setting of partially reliable pieces of evidence subsumes some important combination schemes. So first, if the messages are assumed to be reliable with probability 1, then our knowledge about X reduces as it should to the combination by Dempster's rule of the mass functions M1 and M2. Second, if the messages have independent reliabilities, then our knowledge about X reduces to the discounting of each message according to its reliability, and then combining by Dempster's rule the resulting mass functions. That is, we recover the classical, sometimes called discount and combine scheme. And third, if the messages have dependent reliabilities, and specifically one message is reliable if and only if the other is not reliable, then our knowledge about X reduces to a mixture or weighted average of the messages, where the weight alpha here is the marginal probability that the first message is reliable. Okay, so far we have considered the case of uncertainty about the reliability of the messages. Let us now study the case of imprecision about their reliability. So imprecision means that the reliability is known in the form of some non-elementary assumption capital R, which is a subset of the space of calligraphic ball R. And in this case, our knowledge about X may be defined as the mass function capital Rm, generated by this random set here, where gamma subcap capital R is the mapping representing the fact that if the actual codes were omega 1 and omega 2, and then we know for sure that X belongs to the union of all the elementary assumptions R bold belonging to capital R of the images of these codes and of these assumptions R bold by the mapping gamma calligraphic R bold. And P capital R is the distribution on the codes condition on the pairs of codes that yield non-contradictory interpretations of their assumption capital R. So such imprecise assumption about the message's reliabilities subsumes two important combination rules. So we recover the disjunctive rule by assuming that at least one of the messages is reliable, which corresponds formally to this capital R here. And in the case where we receive n messages, we obtain a rule extended the Q relaxation from interval analysis by making the assumption that n minus q out of the n messages are reliable. So let me remark that both imprecision and uncertainty about the reliability can be taken into account by considering a mass function on calligraphic R, leading to a general model that subsumes the previous ones. But I will refrain from presenting it, as I'm going to present immediately a final model, which is even more general for taking into account various assumptions with respect to the lack of reliability of the messages. So this final model deals with the case of the reliability involving both the relevance and the truthfulness dimensions. So let us first consider a simple situation where we have two pieces of evidence corresponding to two messages, meaning X belongs to A1 and to A2 respectively. And let me introduce the space bold RT, which represents all the possible assumptions that can be made about the relevance and truthfulness of the two messages. So when the messages are assumed to be in some particular joint reliability state are bold here, then it is clear that we should deduce that X belongs to the intersection of the images of their individual reliability states by the mapping pi AIT, which I will denote by pi of R bold, and where the mappings pi AIT here are those that we have seen earlier for modeling the relevance and truthfulness of a single message. Furthermore, similarly as it was the case on the previous slide, for a non-elementary assumption capital R about the messages, we only know that X belongs to the union of the images of the elementary assumptions R bold belonging to capital R. So for instance, consider the assumption that capital R here, that both messages are relevant and that exactly one of them is truthful. Then in this case, from the pieces of information A1 and A2 that we have received, we should deduce that X belongs to the exclusive disjunction between A1 and A2. And actually, what can be shown is that any connective of Boolean logic can be reinterpreted in terms of assumptions on the message's relevance and truthfulness. Okay, so now let us consider the general case of two messages with uncertain meanings and of uncertain and imprecise knowledge about their relevance and truthfulness, which is formally represented by a mass function on the space calligraphic bold RT. So it is useful to remark that any focal set of this mass function yields a binary connective, and that a given connective may be retrieved for different assumptions capital R, so that in effect, uncertain and imprecise knowledge about the relevance and truthfulness of the messages amounts to a probability distribution PB over the connectives to be used to combine the messages. Hence, in this general case, the available information may then be represented by this random set here, where gamma B is a mapping from the join codes and the connectives to the power set of theta, which models the fact that if the actual codes were omega 1 and omega 2, and the messages were in some reliability states corresponding to a combination by connective B, then we know for sure that X belongs to the combination by the set theoretic connective associated to B of the meanings of the messages under this code. And where PB is the product measure of the distribution on the code, so P12, and on the connectives, conditioned on the tuple of code, on the tuples of codes and connectives that do not yield a contradiction. Furthermore, we can show that the knowledge about X induced by this random set here is represented by the mass function Bm, which admits this simple expression here. So basically, we can see that it is the result of a mixture of combining the mass function M1 and M2 according to the possible connectives, weighted by the probability of each connective that has been rescaled according to the overall probability to obtain a contradiction. So thanks to this general approach, able to deal with assumptions about various forms of the lack of reliability, we obtain in particular a generalization of Dempster's rule to all Boolean connectives, which is interpretable in terms of reliability assumptions. And we also have a precedent to understand and the most of the main alternative combination schemes to Dempster's rule, and which can also help us to select the most adapted rule for a given situation. So in practice, alternatives to Dempster's rule offer some flexibility for combining pieces of evidence that can be useful. So indeed, in applications, pieces of evidence may not be all reliable. So here I provide a few samples of examples from the literature, mostly taken from the classification domain, where alternative assumptions about the reliability of the pieces of evidence have been exploited successfully. So the first example is the evidential k-nearest neighbor classification rule from Thierry Leneux, which is arguably the first important evidential classifier. So in this classifier, the basic idea is to consider the nearest neighbors of a test instance and to view them as pieces of evidence about the class membership of the instance. So specifically, a given neighbor's class membership information is discounted as a function of its distance to the test instance. And then these discounted class membership information are pooled by Dempster's rule to yield a predictive mass function for the class of the test instance. So in other words, this classifier relies on the discount and combine approach. Another example from the classification domain is the approach by Zhang and colleagues, where the predictive mass function for the class of the test instance is obtained by considering a set of decision trees, building an evidential prediction for each tree, and then averaging these evidential predictions. In the works of Yang and colleagues, several evidential deep neural networks are considered, each producing a segmentation for a medical image based on a different modality. And the outputs of the networks are corrected using contextual discounting before being combined by Dempster's rule. And finally, it has been shown in the works of Pelicano and colleagues that the Q relaxation rule can be used to improve performance in the presence of outliers. Okay, so let us now consider the second assumption leading to Dempster's rule. So the orthogonal sum M1 O plus M2 relies on the assumption that mass functions M1 and M2 are induced by independent pieces of evidence, which amounts to specifying the joint probability P12 on omega1 times omega2 to be the product measure P1 times P2. However, in principle, any dependent structure and thus any distribution P12 having P1 and P2 as marginals can be selected. And this is illustrated by Shafer in a 1996 paper, where omega I is binary. That is, each message has two possible meanings. So specifically, each message has an interpretation denoted here by the number 1, where it is useless. That is, it means X belongs to theta. And the other interpretation of the first message, which are denoted by 0, is that it means that X belongs to A. And the other interpretation of the second message is that X belongs to the complement of A. And there are some marginal probabilities for the messages to be useless, which are shown here. And the dependency is specified by providing a conditional probability of 0.9 that basically the first message is useless given that the second is useless. So in this case, we have that the joint probability measure P12 is not the product measure P1 times P2. So we can remark that this is an example of non-independence between messages inducing simple mass functions. And what I will actually do in all of this part of this talk on dependence is to focus on the combination of dependent and elementary pieces of evidence, as is the case in Shafer's example, assuming throughout that these pieces of evidence are reliable. So before diving into that, let me briefly motivate why it might be interesting to focus on the combination of simple mass functions. So recall that a mass function is simple if it has two focal sets, so theta and some strict subset A of theta, which means it is of the form m of a equals 1 minus d, m of theta equals d for some d in the unit interval. So it represents a message that means x belongs to a with probability 1 minus d, and that is useless. It means x belongs to theta with probability d. And a prototypical example of this is a sensor reporting x belongs to a and assumed to be faulty with some probability d. And these simple mass functions are considered to be the simplest kind of evidence, hence their name. And as a matter of fact, Shafer and Smets propose solutions to recover belief functions or to view belief functions as resulting from the combination of such elementary pieces of evidence. And furthermore, in applications, belief functions often result from such combination. So they are simple, yet they play central roles, both from a theoretical point of view and in applications. And as we will see, by focusing on the combination of such elementary pieces of evidence and relaxing the usual independence assumption, we are able to obtain some further results, both on the theoretical and application sides. So specifically, it will allow us first to bring to light a theoretical result about belief functions, which is a canonical decomposition for a belief function. That is a unique decomposition of a belief function into simple mass functions. And then it will allow us to improve an evidential classifier that has been recently introduced. Okay, so let's get into it. So the general setting that we will consider is the following. Let M1 to Mn be simple mass functions. So we assume that mass function Mi is induced by the message omega I pi gamma I with omega I equals 0, 1, pi of 1 equals di, and gamma I of 0 equals ai, gamma I of 1 equals theta for some strict subset ai of theta and some di in the unit interval. So this mass function mi is of the form mi of ai equals 1 minus di, mi of theta equals di, which I may denote for short ai di. Furthermore, we denote by Si the variable with state space omega I, representing the possible interpretations for the ith message. Now, assume this message has some dependent structure described by a joint probability distribution P1 to N for variables S1 to Sn, defined on bold omega, which is the Cartesian product of the omega i's. Furthermore, assume that these messages are reliable. Then, under the preceding conditions, it is clear that knowledge about X is represented by the mass function M1 to N, induced by the random set composed of capital bold omega, probability measure P intersection, and mapping gamma intersection, where this mapping gamma intersection is the same as the one involved in Dempster's rule and corresponds to the assumption that the messages are reliable, and where P intersection is defined similarly as in Dempster's rule, that is, it is nothing but the joint distribution P1 to N, and the interpretations condition on those interpretations that do not lead to a contradiction. Now we can make the easy remark that if the messages are assumed to be independent, then distribution P1 to N is the product measure of the marginal distribution PIs, and mass function M1 to N is simply the result of combining the simple mass functions AI di by Dempster's rule, and is therefore separable. So in this setting that we are considering, the joint probability distribution on the interpretations of the messages is represented by a multivariate Bernoulli distribution. And Tuggles has shown that such a distribution is characterized by the means of the variables Si, which are nothing but the marginal probabilities di that the messages are useless, and by the central moments between these variables, which can be conveniently indexed using all the possible binary vectors omega, bold, such that the sum of their components is greater than 1. So there are 2 to the power of n minus 1 such central moments, and they represent the dependencies between any subsets of all the variables Si, and it is convenient to store them in a vector in some chosen order, such as the binary order, which is called the dependence vector by Tuggles, and which we denote here as sigma bold. So in sum, what we see here is that given some messages that have 2 interpretations each, any dependent structure between them is fully described by a vector of central moments between their interpretations. So based on what we have just seen on the multivariate Bernoulli distribution, we can revisit our setting. So let omega I, pi, gamma I be messages representing reliable and elementary pieces of evidence about X, inducing simple mass functions mi equals ai di. Assume they have a dependent structure described by a vector sigma of central moments. The mass function m1 to n is representing knowledge about X given this species of evidence, is then induced by the random set, so bold omega p intersection gamma intersection. With p intersection, the probability distribution characterized by the vector sigma and condition on the event theta intersection. So this leads us to the following definition. Let a1 d1 to an dn be simple mass functions. Their sigma sum is the mass function denoted O plus sigma of a1 d1 to an dn and defined as the mass function m1 to n defined above here for the given vector sigma and the given simple mass functions ai di. Okay. So the sigma sum of n simple mass functions represents thus the knowledge on X if we assume that the simple mass functions represent reliable and elementary pieces of evidence having some dependence characterized by dependence vector sigma. And let me also remark that when vector sigma is a null vector, then we have that the distribution P1 to n is the product measure of the PIs, and thus this sigma sum reduces to the orthogonal sum. So let me illustrate this operator with Shafer's 86 example. So in his example, the pieces of evidence are represented by the simple mass functions a sub 0.2 and complement of a sub 0.01, respectively. And using the formalism I have introduced, the dependence between these pieces of evidence can be characterized simply by the central moment sigma 1,1 between the variable representing their interpretation, which is nothing but their covariance, and which is equal, in this example, to 0.007. So in this example, we have that the knowledge induced about X given the pieces of evidence and their dependence is represented by the 0.007 sum of the simple mass functions a sub 0.2 and complement of a sub 0.01. And it does not really matter, but for completeness, I provide here the result of the combination of these two pieces of evidence given their dependence. Okay, so what is particularly interesting with this combination rule is that we can show this theorem, which basically says that any mass function m is obtained uniquely from k elementary pieces of evidence represented by simple mass functions, assumed to be reliable and to have some dependence characterized by some dependence vector sigma bold, which is nothing but the dependence vector of a k-variate Bernoulli distribution obtained in some particular way described in the statement of the theorem. And furthermore, given the remark below, we have that each of these elementary pieces of evidence points to the complement of an element of theta with support 1 minus the plausibility of this element. So this decomposition is illustrated numerically here with some mass function defined on a ternary space. So here you can see that the vector sigma is composed of 4 components, since the decomposition of M into elementary pieces of evidence involves a trivariate Bernoulli distribution, and the dependence in such a distribution is fully described by 4 central moments. You can also see that the simple mass functions in the decomposition are obtained from the contour function. So for instance, you have this value 0.8 here for the simple mass function focused on the complement of theta 2, because the plausibility of this element is 0.8. So this decomposition is an alternative solution to that of Shafer and Smets for recovering belief functions from elementary pieces of evidence. So since it is not possible to recover all belief functions merely from independent pieces of evidence, which is only to the class of separable belief functions, our approach is to consider that they may be dependent. So it is a simple yet arguably natural approach in the sense that given that elementary pieces of evidence represented by simple mass functions amount to marginals of some joint probability distribution, and we know that assuming independence only gives you one of the possible joints, then it may be expected that an arbitrary belief state represented by a belief function requires some dependence between the elementary pieces of evidence in order to be recovered. And in any case, it is a much more conventional solution than Smets, which involves the notion of debt of belief, represented by generalized simple mass functions whose masses may lie outside the unit interval. And it is quite a quite different solution from that of Shafer's, which involves the coarsening and limits, and which was criticized by Smets. Okay, so this last part of my talk is about an application of being able to account for the dependence between elementary pieces of evidence inducing simple mass functions. So this application requires to handle the dependence between only two simple mass functions, and even a bit more precisely between two particular simple mass functions, which we will see later. And to handle the dependence between only two simple mass functions, I am going to use a slightly different formalism than the one we have seen so far, in which I'm going to explain right now. So let omega 1 P1 gamma 1 and omega 2 P2 gamma 2 be two messages representing reliable and elementary pieces of evidence about X, inducing simple mass functions M1 and M2. So we have seen that given D1 and N2, the joint distribution P12, and thus the dependence, can be specified by providing some covariance between the interpretations of the messages. But alternatively, the distribution P12 may be specified simply by providing the just probability that the two messages are useless. Now, specifying this probability, given the marginal probabilities of the messages being useless, actually amounts to specifying the dependence between these events. And it happens that, that this dependence can be completely characterized by a scalar between -1 and 1, presenting the correlation between the events. And in particular, a model of correlation between two events of probabilities P1 and P2 with correlation R is provided in this reference by Ferson and colleagues. So it is based on the Frank family of copulas, and it is such that the probability of their conjunction is equal for correlation R to the quantity F of P1, P2, R, with this quantity being defined by this equation. So we can remark in particular that for R equals 0, it corresponds to the case of independence. So in sum, what we have here is that the dependence between two elementary pieces of evidence can be characterized by a correlation R. Okay. So based on this observation, we can introduce a combination rule for two elementary pieces of evidence relying on the correlation R to represent their dependence as follows. So let P intersection R be the result of conditioning distribution P12 on the event theta intersection, and where P12 is specified by providing the dependence between the messages being useless using correlation R. Then we have that the knowledge about X given the messages omega 1 P1 gamma 1 and omega 2 P2 gamma 2, inducing the simple mass functions M1 and M2, assumed to be reliable with dependence characterized by R, is represented by the mass function induced by the random set based on the distribution P intersection R, P intersection R, yes. And I will call this mass function the R sum of A1 D1 A2 D2 and denote it A1 D1 O plus R A2 D2. So this binary operation O plus R here is a generalization of Dempster's rule, which is recovered for R equals 0. So as I mentioned earlier, the application in which I am going to use this operation involves some particular kind of elementary pieces of evidence. These are known as positive and negative pieces of evidence for a proposition, which are defined like this. So positive and negative pieces of evidence with respect to a proposition X belongs to A are elementary pieces of evidence inducing simple mass functions with focal set A and focal set complement of A, respectively. So for instance, our example taken from Shafer's paper is a case of positive and negative evidence with respect to a proposition. And for completeness, I provide this proposition here, which gives the result of the R sum of a positive and negative piece of evidence for proposition A. And the expression you see on the right is, of course, a generalization of the expression of Dempster's rule. Okay, so now that we are equipped with this rule to handle a dependence specified by correlation R between positive and negative evidence for a proposition, I will present some recent works where we have used it to improve an evidential classifier that was recently introduced by Huang and colleagues, and that is an alternative to the prototype-based improvements proposed by Thierry Deneux in 2000 of the evidential generous neighbor classification rule that has similar properties. So this evidential classifier was obtained by applying ideas developed in this paper by Thierry, which brought to light a mass function underlying the logistic regression. So applying these ideas to a radial basis function network, RBFN, with a softmax output layer in the case of multi-class classification, or logistic output unique output unit in the case of binary classification. And I will call hereafter this classifier the evidential RBFN, or eRBFN for short. And it was used in this paper here to enhance the predictions of a unit model for a task of lymphoma segmentation from 3D PET-CT images. So in essence, the eRBFN reveals a predictive, so-called latent mass function MU underlying the probabilistic prediction PU of a given RBFN with a softmax output layer with respect to the unknown class X of an instance with feature vector U. So the mass function MU underlies PU in the sense that its approximation by a Bayesian mass function, in other words, by a probability distribution, using the possibility transformation method, is exactly PU. So here is the definition of this method. As you can see, the approximation of a mass function M is obtained simply by normalizing its contour function. So in a nutshell, the mass function mu is obtained by first defining positive and negative pieces of evidence, denoted here mk plus and mk minus for each class of theta k, based on the parameter of the RBFN and on the vector u, and then pulling them by distance rule. So that is formally mu as this expression here. Okay. So in the eRBFN, the positive and negative evidence for a given class are considered independent since they are combined by Dempster's rule. However, they are obtained from the same set of values, and therefore the independence assumption may be questioned. So when pulling the positive and negative evidence for theta k, it seems safer to assume that there is some dependence between them. And as we have seen, such a dependence can be characterized by a correlation, which I denote here Rk. And our first result with respect to the eRBFN is the following. Let mu r-bold for some vector r-bold of k correlation be the mass function defined similarly as mu, but where the orthogonal sum of the positive and negative evidence for class k has been replaced by the Rk sum. Okay? And the result is that we have that the approximation of this mass function is nothing but the prediction of the RBFN. So the independence assumption made in the eRBFN for each class is actually inconsequential insofar as any possible dependent structure yields a predictive latent mass function. That is a predictive mass function whose plausibility transformation is PU. And thus, we have brought to light a set of latent mass functions for RBFN. Now, of course, the dependent structure chosen for each class, those have an impact on the predictive mass function, and therefore those matter. So which begs the question, which vector of correlations are we should use for any given test instance. So one possibility, assuming some learning data are available, is to select the vector of correlations which will tend to yield the best uncertainty quantifications, that is the least loss for some loss L of an evidential prediction mu for an instance with feature vector u and true class X. And an appropriate such loss was recently proposed by Thierry. It is called the generalized negative log likelihood, and it is defined by this equation here. So it is a criterion that generalizes the typical loss for probabilistic predictions and whose minimization amounts to seeking high degrees of belief and of plausibility for the true class. So to illustrate the interest of this approach, which is meant to produce more sensible predictive latent mass functions for RBFN, according to the principle of minimizing the loss, we conducted the following numerical experiments. So we used 4 real datasets considered in related works, so PIMA and ionosphere, which are binary classification datasets, and GLASS and Voyal, which are multi-class classification datasets. And for each dataset, the data were split randomly into training, validation, and test sets, containing respectively 60%, 20%, and 20% of the instances. So the training set was used to learn the RBFN, the validation set was used to optimize the vector of correlations, and the test set was used to evaluate the performance of the optimized vector correlation, as well as the vector, the null vector for the correlation, which corresponds to the original proposal by Yuang and colleagues. And this process was repeated 50 times. So here you can see box plots of test GNLL values for the 2 binary classification datasets. So for each dataset, you see on the left the results of the eRBFN, and on the right those of our proposal, which is an extension of the ERBFN accounting for the dependence between positive and negative evidence for each class. And here are the results for the multi-class classification datasets. So we can see that for all 4 datasets, we outperform the original ERBFN. And actually, all these differences are highly significant according to paired t-tests. So to sum up this talk, we have first recalled that Dempster's rule follows from assuming that the pieces of evidence to be combined are reliable and independent. And then we have seen that we can extend this rule to other assumptions. So specifically, we first saw a general fusion approach allowing us to handle various alternative assumptions about the reliability of the pieces of evidence, and in particular, allowing us to obtain an interpretation of Dempster's rule generalized to all logical connectives. Subsequently, we covered an approach for the fusion of dependent elementary pieces of evidence, allowing us to describe the dependence structure through some interpretable quantities, so a correlation in the case of 2 elementary pieces of evidence and central moments in the general case, and allowing us to obtain an interpretation of belief functions, which is in the spirits of that of Shafer and Smets, in the sense that it is based on the combination of reliable elementary pieces of evidence. And specifically, we show that any mass function can be seen as resulting uniquely from some reliable elementary pieces of evidence having some dependencies. And in addition to these theoretical results, we also demonstrated the applicability and practical interests of these approaches through some applications. And one last thing I would like to mention is that if you need to combine partially reliable and dependent pieces of evidence in some applications that involve some continuous variables, then you are lucky, as a very thorough treatment of this problem has just been published by Thierry in an article, which I recommend. So here are the references to my own works that support this presentation. And here are the various references to other works that I mentioned along my presentation. Thank you for your attention.